Welcome, and thanks for joining us. I'm Linda Bell, Editorial Director at Tech Briefs Media Group, and I'll be your moderator for today's webcast, Spacecraft Thermal Management, Board, Box, and System-Level Solutions, sponsored by Advanced Cooling Technologies. Today's webcast will last about 30 minutes, and there will be a question and answer period at the end of the presentation. You can submit a question anytime by entering it in the box at the bottom of your screen. Our presenters will answer as many questions as possible, and those questions not answered during the live event will be answered following the webinar. In order to view the presentation properly, please disable any pop-up blockers you might have on your browser. Let's meet our speakers. Brian Musica is Sales Manager for Advanced Cooling Technologies, Defense, Aerospace, and Custom Products Group. He worked as Research and Development Engineer for ACT's Aerospace Products Group before taking on his current role. He is responsible for product and technology sales across numerous industries. Jens Wyant is Manager for ACT's Defense Aerospace Products Group, which handles design, prototyping, and production of embedded computing thermal solutions. He's worked for ACT for 10 years in R&D, product development, and production. He's contributed to thermal solutions for embedded computing, radar, power electronics, direct energy weapons, and spaceflight components. So now I would like to hand the program over to Brian Musica. Brian?
Thank you, Linda, and thank you all for joining us today. Satellite thermal control is a hot topic right now. There are full conferences and workshops dedicated to this topic, so I guarantee we won't touch on everything related to satellite thermal control, but our goal here today is to give you kind of a basic understanding of the options available to you, mainly in the passive heat transfer realm. Just a quick overview of advanced cooling technologies for those who might not be familiar with our company. We were founded in 2003 and are located in Lancaster, Pennsylvania. We have 60,000 square feet here, so we're a small business operating in Lancaster, Pennsylvania. Our focus is in thermal management, so we have a large range of thermal management solutions. Our primary industries are satellite thermal management, obviously, as well as terrestrial defense, industrial products such as the medical or power electronics markets, HVAC, and we have a line of enclosure cooling products as well. We have a large engineering force, so we have a lot of work in research and development, and we have the capabilities to take solutions from concept, design, prototype, all the way through full-scale manufacturing. And we are governed by ISO 9001 and AS 9100 certified quality systems. Now, jumping into the topic, just some high-level thermal considerations for space applications. The first is that obviously in space there is no air, so you're relying on radiation as your ultimate heat sink. With that, to be as efficient as possible, you want the radiators very isothermal, and you also want them operating at as high a temperature as possible. The counter to that is you want to make sure that your electronics stay below their max operating temperatures. So the key there is to really have a strong, as low as possible thermal resistance network, so getting heat from the source component to the radiators with as small delta T as possible. The other consideration, not unlike other systems, but probably more key in space, is that reliability is a very key factor. So we can't send up maintenance people to space to service these satellites, so making sure that you have a good grasp on the mission life and that all your components are rated for longer life than the mission, and anywhere you can avoid moving parts or potential failure mechanisms is key. And the final one is having a low mass and volume. So launch vehicles are only so big, and it's more costly to launch more massive systems. So creating a low mass and low volume system is often favorable. Now, today we'll touch on mainly principles that can govern across many different sized satellites, but two areas we want to kind of touch on or highlight is within the CubeSats. The The goal here in CubeSat applications is to get the heat to the edges, the sidewalls of the CubeSat, which would double as radiator panels. The other area, which is the larger satellites, is the geosynchronous orbit satellites. And there they have more complex thermal designs where they typically have electronics boxes coupled to payload panels or cold plates, and then larger thermal management systems that take it out to external radiators. So in either case, transferring heat efficiently is key, but we just wanted to give you an idea of some of the different scales in satellite applications. And this is just a small sample size of what's actually out there on the market. There are nano satellites all the way up to these very high power satellites. So on slide 5 here, we're going to kind of give you an overview of some passive technology options. And maybe at this stage, we'll take a quick pause, because what we're going to do in this webinar, which is somewhat new for ACT, is at the end, after we introduce these various technologies, we're going to actually ask a quiz question to the audience. And those who get it right, we're going to randomly select, and we'll award a gift card to a couple people that get the question correct. And anyone who answers and gets it correct, we are going to send a heat pipe sample to. So we urge you to pay attention, stay till the end, and hopefully get the question right. But just looking at some passive technology options, the first option, and always the best option if it's going to work for you, is just straight metal conduction. So here the operating principle is that you're governed by the thermal conductivity of the base metal itself. So oftentimes you'll be somewhat limited by that thermal conductivity. What's typical in space applications is you want a very lightweight metal, so composites or titanium are often used that have very low thermal conductivity. Probably one of the better mass to thermal conductivity is aluminum, so that's used frequently within the industry. But oftentimes you will have thermal gradients across your metal from the limiting factors of the thermal conductivity value. The second is thermal straps. These are used pretty widely in the satellite industry, and very similar to metal conduction, they're relying on the thermal conductivity value, but they do have either a braided structure or some flexibility to them. So they're used a lot where you're mounting components to areas that might have some shock and vibration isolation required, or some deployability where you need some flexibility in relation to two components. So those are both standard kind of conduction factors, and then the ones we'll kind of go into more detail today are technologies looking at two-phase heat transfer. So we have 3 technologies listed here focusing on liquid to vapor heat transfer, mainly heat pipe technology. The first one is copper water heat pipes. If you watched other ACT webinars, you probably have seen copper water heat pipes in good detail. But they are a passive two-phase heat transfer device, so very reliable. And they're good in a satellite world for board and box level heat transfer, so short distance or higher heat flux heat transfer compared to some of the other solutions. The second is aluminum ammonia. So again, similar operating principles to the copper water. This is used in the industry for more system level heat transfer. So on some of those larger satellites, getting heat out to the radiator panels and embedding within the radiator panels to isothermalize. And the final heat pipe one that we'll touch on just very briefly is other working fluids. Because there are various missions in space that might have lower operating temperatures or higher operating temperatures, we did just want to touch on that there are other fluid options available for those types of missions. And the last technology we'll touch on is phase change material. This is a solid to liquid phase transition that uses the high latent heat of fusion of a material to absorb energy. And this would be appropriate for those applications that have a duty cycle associated with them. So with that, we'll kind of go through the various heat pipe technologies. So first, before we jump into specific heat pipes, we'll talk a little bit about the theory. And again, if you want to learn more about heat pipe theory, there's a lot of information on our website, and we've done previous webinars. So I'll just touch through today at a high level and then mainly focus on practical space applications. So a heat pipe operates in two-phase, liquid and vapor. And what happens inside the heat pipe is you are vaporizing a fluid by introducing power to the heat pipe. So your electronics are coupled with the heat pipe. They introduce power, which vaporizes the fluid internally. That fluid pushes to wherever it's colder in the system. So you have vapor flow inside the heat pipe, and you release the latent heat wherever it's colder. So at the condenser end in the figure, you release the latent heat of the vapor, and you condense it back to a liquid. And then there's an internal capillary force or a wick structure that drives that liquid back to the hot region. But overall, you get very efficient heat transfer, and it's passive, so highly reliable. So it's pretty ideal for space applications. Now, looking at copper water heat pipes, water is a very favorable working fluid. So especially for most electronics closer to the max temperatures of electronics, it's a very favorable fluid at those temperatures. It also has the ability to handle high heat flux compared to other fluids. So it can handle up to 50 watts per centimeter squared with traditional wick structures. And we've actually designed unique wick structures in planar heat pipes or vapor chambers that can handle up to 1,000 watts per centimeter squared. So there are options to exceed even the 50 watts per centimeter squared. Overall, it's very easy to integrate into your system, so they could be bent, flattened, and routed as needed. And they are passive operating, so they are highly reliable, and 20-plus year flight life is not unheard of. For ACT, just to give you an idea of some of the capabilities, we manufacture copper water heat pipes very routinely, and we have the capabilities of manufacturing up to 250,000 per year across all our product lines. For the space industry, it's only a small subset of that based on those applications that have those high heat fluxes. But we are qualified, and we have had our first launch last year. But copper water heat pipes in general have been flown in space flight even before that. One of the first questions we typically get on copper water heat pipes is, because everyone's familiar with water as a working fluid, what happens in those space environments when the temperature drops down below zero? And it's a very good question, something we've addressed in detail during qualification and acceptance test regimen. But what happens within the heat pipe is that the fluid will be absorbed within the wick structure, and that wick structure will act as a sponge and allow for that expansion without causing damage to the copper envelope. So we have demonstrated freeze thaw tolerance, and going down the list, we've also demonstrated shock vibration tolerance and have done a lot of testing to some of the MIL standards and aerospace standards that are out there. They can also be externally coated for environmental protection. So a lot of times in space applications, you want something like a chem film to be environmentally sound and to adhere to other materials in the higher level assembly. And I'm not going to go through each of these products in detail, but I will point out the middle product. This is the product that was launched on our initial NASA flight. So it's a copper water embedded aluminum plate. It has 9 heat pipes in it, and that's one that does have flight heritage. So moving on to HighK or high thermal conductivity plates, this is the application of embedding heat pipes into an aluminum base plate. So at ACT, we routinely do this for the space industry to get a really high heat transfer plate. So compared to aluminum, it gives you about 3 to 4 times the effective thermal conductivity without sacrificing weight and without sacrificing structural strength. So because you want to use as much of your satellite as possible for thermal dissipation, it's a really nice member that can be used both structurally and thermally. And now we'll kind of point out the bottom right figure here. This is one unique design that was about 2 feet by 3 feet, and you can see the gray areas is the solder interface above the heat pipe. But we strategically laid the heat pipes in there to take care of some significant hotspots on this plate. And on the next slide, we're going to go into a video actually comparing a base aluminum plate to this high thermal conductivity plate to give you an idea of the benefit of heat pipes. So hopefully that video gives you a good sense of what's possible with a HighK solution. The next area we're going to go to is some practical applications that are useful for CubeSat and avionics boxes associated with satellites. So the first is HighK board frames. These are used to transfer heat from electronics components mounted on a PCB that's integrated into your chassis in an avionics box or your CubeSat directly. And the goal here is to spread heat out to the edge as efficiently as possible and also transfer heat along the edge so that you lower heat flux into your higher level thermal assembly. I'll jump down to the bottom one, which also uses HighK technology. So once you get the heat out to the edge, then the goal is to isothermalize your next higher level assembly. So in the sense of a CubeSat, you might be getting it directly out to your sidewalls, which serve as the radiator panel. And if you make those radiator panels a HighK plate, you'll isothermalize them and get better rejection. On the other case, for larger satellites, you might be transferring heat to a cold plate along the base of your chassis or avionics box, and in which case there, what you want to do is use heat pipes to route the heat down to that cold plate and potentially along the cold plate to lower the heat flux into the higher level assembly, which could be an ammonia-based heat pipe, which has some heat flux limitations. So now jumping back to the middle bullet point there, this was not included in the initial technology overview, but does have some application for satellites that use wedge lock mechanical retainers. So ACT actually just recently was awarded a patent for the ice lock, which is a improved wedge lock, and it could fit into very similar form factors as the COTS versions available. But overall, it gives you about a 30% improvement thermally at that connection, which is often looked at as a thermal bottleneck. And we won't go into too much detail here on their operating, but we did a couple months ago release a webinar very dedicated to the ice lock. So if you're interested, I'd encourage you to check that out or reach out to us with any questions. So moving on from copper water, the next solution we want to talk about is aluminum ammonia CCHPs. So ammonia is a very compatible working fluid with aluminum, which helps for weight purposes at the system level. So these have been designed and implemented into satellites for decades and are TRL-9 and can provide very good heat transfer at the system level. So these can be manufactured in upward of 10, 20 feet in length to take heat from your payloads externally to your radiators, and then they're also used in like aluminum honeycomb radiators to isothermalize and make sure that your radiator is operating at peak efficiency. They can be designed into 2D and 3D configurations, and they are fairly flexible, similar to copper water pipes as far as how they can be integrated and designed into your system. One thing to consider with the ammonia-based CCHPs is the wick structure and fluid properties associated with it. So with the long-distance heat transport requirements, we utilize a grooved wick structure, and so that's really good for moving the fluid long distances, but it does not create as high of a capillary pressure as some of the other wick structures might. Coupling that with ammonia, which has fairly poor surface tension, these cannot wick against gravity very well. So although they operate very well in microgravity space environments, it's difficult to do ground testing on these systems. So one of the industry standards that have been developed over the year is to test these 1/10 of an inch adverse orientation. But this is one of the big benefits for some of the box level going with the copper water, because those are ground testable and can wick against gravity. The other area I mentioned early on talking about copper water is some of the limitations of ammonia as far as heat flux is concerned. So again, because of the wick structure and the fluid, the heat flux limit for ammonia is about 5 to 10 watts per centimeter squared. And that is usually acceptable for the satellite industry, so there's usually not too much of an issue with those heat flux, but it does make it important for the box level design and the cold plates to make sure that the heat flux is within that limit before you're taking heat off to the radiators. But all in all, it does give you very long distance heat transport and pretty capable designs. You can see one, this is a 1/2 inch single board design on the bottom right, and you have the transport capacity there. but these are very scalable, similar to copper water, where we have lots of options in terms of diameters and flexibility within the design. So now moving on from ammonia, we just wanted to have one slide in here talking about other fluids, because the space industry does have a lot of unique requirements for lower operating temperature fluids. So the figure of merit is a heat pipe selection guide to fluid selection, and it kind of ranks fluids based on how well they'll perform in a two-phase heat pipe setting. So you can see the top two there are actually the water and ammonia designs, and if you're shifting to the left and you were looking at a lower operating temperature, you might want to go with like an ethane or propylene, both of which have been flown in flight. Now we're shifting gears to phase change material, which is a solid to liquid phase change. And so we'll do a similar kind of technology overview with that, and mainly focus on where it could be applied in space environments. So PCM, if you're not familiar with it, has a very high latent heat of fusion, much higher compared to the specific heat. And if you look at the figure on the right, you can see during that latent heat, which is the phase transition period when you're going from a solid to a liquid, you can basically maintain temperature or have very low temperature rise with a steady heat input. So it's really nice for applications that operate with a duty cycle, where you can melt and then refreeze during the off cycle, or things like a very short duration mission. The challenges with PCM is that it has very low thermal conductivity, so it makes it very important that you design the internal support structure properly to conduct heat within the PCM. And I won't go too much into PCM selection, but there are several options. Probably the most widely accepted for space industry has been the paraffin wax, which has a lot of cycling data and does provide good mass efficiencies. Salt hydrates have the challenge of being corrosive, and metals tend to be a little more massive. So I kind of already touched on when to use it. The reason to use PCM is because it's reliable and passive operation again. But the big benefit for these space applications is if you are operating on a duty cycle, you can size your ultimate heat sink for average heat load instead of peak heat load. So you get some weight and volume benefits at the radiator panel or metal conduction levels by absorbing that heat at the component level. So in space operations, that especially LEO, low Earth orbiting operations, where you might only be sending out signal during certain periods of the orbit, those tend to be really good applications where PCM can absorb that energy. So qualifying PCM for the space industry, we talked about the importance of the design side, making sure your internal structure can melt the PCM properly, and also selecting the right PCM. On the manufacturing, it's a very quality intensive process, making sure everything's cleaned out well, it's all sealed up well, processed well, so that you can contain the pressure inside, as well as not vent out any PCM over the life cycle. But probably the most important is the qualification testing. So there's items that we have in-house, such as the differential scanning calorimeter to kind of determine the validity of the PCM. We do thermal cycling to show that it's going to stand up over the lifetime, and also do transient thermal performance tests to make sure it'll melt and then re-solidify appropriately. And with that, I'm just going to touch on, or pull up here the options that we talked about, but we're going to jump into the case study here and open it up to the questions to the audience. So hope everyone has a good sense of what these technologies can do and can answer the question. So the case study we're going to look at is a CubeSat application that generates over 1 kilowatt of heat. The heat flux, there's several components that generate that 1 kilowatt, each operating about 25 watts per centimeter squared. The max temperature that you must keep the components under is 75 degrees C. The operation is 30 seconds on and 30 minutes off. And the dimensions, it's a 6U CubeSat, so it's about 12 centimeters by 24 centimeters by 36 centimeters. And the ultimate heat sink is the sidewalls, and they are aluminum based. So now we'll pull up some options for you to take your quiz. All right, I hope everyone had a chance to answer the question. So now real quick, we'll kind of go into this case study and go through the design a little bit, and then hopefully summarize real quick and allow you guys to ask some questions. But basically the three drivers of this selection is the total power. 1 kilowatt is a lot for space applications, so it'll likely require more available radiator volume that you had, which may become problematic. The second is that it operates under a duty cycle, which was pretty severe, so 30 seconds on and 30 minutes off is a long time. So utilizing a PCM in there could ultimately allow you to hit your radiator size. And then the heat flux was fairly high, so it was higher than ammonia could handle, so copper water is probably the appropriate heat pipe selection to transfer heat to the ultimate radiator panels and couple with the PCM. So hopefully everyone answered that right, and now we'll kind of dive a little deeper into what we would look at and go about designing this. So the first, once we determine that PCM would be a good solution, we'd look at the desired melt temperature, and that would be somewhere below your 70-degree max operating temperature with a good margin in there. So we'd pick a PCM in that range, look at the material properties, and then determine how much we would need of the PCM. So to determine how much you would need, you look at the power and duty cycle and figure out how much energy storage you would need. In this example, it was around 60 kilojoules of energy storage. From there, you can compare the amount of PCM versus the amount of radiator panels you would need. And because the power was so high and the duty cycle was so low, this was a win for PCM. And then you got to figure out where you're going to locate your PCM and how you're going to transfer heat into it. So understanding the geometry of your CubeSat as well as the conduction paths within your PCM is important. And finally, you want to ultimately reject your heat to deep space, so making sure you get your heat to the available area for radiation. So looking at more of the detailed design steps that we would go through, the first would be to design the internal structure of the PCM. So typically we'll use metallic fins in those areas. If the volume is so large that you need more enhanced conduction, we could actually look at incorporating heat pipes within the PCM. Then we would run some transient analysis to make sure the PCM is going to work in the system. And finally, if that's showing well, we'll design back in the external mechanical features to integrate it within your satellite. On the heat pipe side, we're going to determine the size and number of heat pipes based on the power requirements. We're going to determine how we're going to attach them, typically by a solder or epoxy method. And then we'll model them accordingly. And we have some tricks on our website to model heat pipes. But basically, you want to get the heat pipe to within 2 to 5 degrees C from hottest point to lowest point, so you can insert a bulk thermal conductivity and kind of adjust it until it meets that goal. And on the figures there, you can see the both the thermal analysis we did in the top right, showing the PCM absorbing the energy and the radiators dissipating, and then on the bottom right, the max temperature of the base, which you can see here was able to stay with it below the 70 degrees C for upward of 40 seconds operating, so you had some margin there if the requirement was 30 seconds. So just to summarize, I know we covered a lot here, but Spacecraft design is fairly unique, and there's a lot of intricacies that go into it because of the uniqueness of the environment. Ultimately, you want a highly reliable and passive solution that can get you long mission life, very lightweight. So two-phase products that are closed loop are pretty ideal. And the two technologies we covered in detail, phase change material is a strong solution for thermal storage, and heat pipes are a strong heat transfer device. So just one last slide here before we open it up for questions. I just want to touch on a couple other technologies that we get a fair amount of interest in from the space industry. So I won't go into detail, but again, there's a lot of information on our website, and feel free to reach out to us if there's any more questions on any of these technologies. Variable conductance heat pipes is a unique heat pipe where we actually can control or maintain temperature at the evaporator. So the way we do that is introduce a non-condensable gas, which will expand and contract into a reservoir. So it'll expose or remove portions of your condenser, which will allow you to maintain temperature at the evaporator. So this is used frequently in the space industry for survival to eliminate or reduce the amount of survival heat required. Loop heat pipes are one of the most capable heat pipe technologies out there. They can move very high amounts of heat, up to 1 kilowatt of heat, and transport it over very long distances. So all the technology is in the evaporator zone, which creates a passive pump, and then you can pump that fluid out to the radiator panels. And all the condenser lines are very straightforward tubing, so it allows for flexibility for deployable radiators or things of that nature as well. Fluid accumulators, this is a way to manage pressure in pump systems, and this is something that we have flight heritage on the International Space Station and are familiar with all the requirements that go into these systems. So it utilizes a bellows chamber to manage and control fluid inventory. And the final is liquid cold plates. So kind of along the same lines as the accumulators, this is a pumped liquid system to cool electronics. And again, we've designed and built these for space flight. So with that, we do have a final slide here on resources. And if anyone's interested in the slides, please reach out to us and we'll send you this that has the link to everything. But I want to thank everyone for your time. I'm sorry we're running a little late here. But thank you for your time, and please feel free to ask any questions.
Great. Thank you, Brian. We do have time for some questions. Our first question is there a certain power where you should start looking at heat pipes over metal conduction?
Sure. That's a bit of a complicated question. It really depends on the system level and how far you need to conduct the heat, how much heat is being generated, and what the heat sink is. So for this one, I'll focus more on the CubeSats, like Brian mentioned on slide 11. So we've seen that at the box level or at the CubeSat level, that when processors are getting around the 15 watt or greater heat load, the conduction path really starts to be a bottleneck, and we see some benefits from using copper water heat pipes. So that will help reduce the gradient out of that box, but also reduces the heat flux if you're mounting that box to a higher level CCHP panel. Okay.
Our next question is, what is the lifespan of a PCM?
That's a good question. So like Brian mentioned, there are a few different phase change materials we can select, paraffin, salts, or metals. So I'll focus on the paraffins for this one. So fun fact, the word paraffin has Latin roots meaning low reactivity, which means it's very stable. So that's why it's used so often for aircraft and spacecraft applications. I will say that it is still a hydrocarbon, and it can be broken down by bacteria and fungus. So it is very important that cleaning procedures are in place to make sure that it's incorporated into the solution cleanly and without contamination. So it's very similar to some of the processes used for fabricating heat pipes, and we make the PCM assemblies here in the same area that we make the heat pipes, and with very similar procedures. Some vendors publish data on their specific blends. There's not a whole lot of data available out there for the pure PCM. So we do have an in-house DSC, a differential scanning calorimeter. We can measure the latent heat initially. We have some custom tooling to thermally cycle it very quickly, and then repeat the DSC scans to measure that latent heat. So we have some data on a little small library here of up to 20,000 cycles for different paraffins.
Okay. And our last question we have time for is, do you coat heat pipes that are exposed to the space environment?
We do sometimes. So let's say for the aluminum and ammonia pipes, if it's being embedded into a panel, we'll incorporate a BR coating to help with that panel adhesion. Sometimes we also use a chem film on those. For copper water heat pipes, we can nickel plate them. But usually corrosion isn't a big concern for space flight applications. Just use some caution if you're testing below ambient and there's a risk of condensing on the parts. You may want to consider a coating for that.
Okay, great. Thank you both very much. I'd like to thank you and all of our audience members today for attending. Just a reminder that this webcast will be available on demand for 12 months at www.techbriefs.com. Thanks again, and have a great day.